We started off our PlayPosit with a video on Pascal's triangle, so we'll look at that a little bit more closely in class. This video is going to concentrate on combinations, and in combinations, order is not important. When we were working with permutations, it was. Be sure to pause the video and put in our new formula. You can use either one. I just changed the denominator order from the first to the second. The only thing different from permutations and combinations is now we're multiplying by r factorial. All right, in this story problem, Ms. Maziere is looking for some volunteers to help her with recycling, and she only needs 3 of the 10 students that are willing to help her. Because order doesn't matter, we're going to be using combinations. We have 10 possible volunteers. We only need 3. So our numerator is going to be 10 factorial. Our denominator, I wrote it as 3 factorial, 10 minus 3 factorial. So that's going to come out to 10 times 9 times 8 times 7, and I'm going to write 7 factorial, and I'll explain that in a moment. And our 3 is 3 times 2 times 1 times our 7 factorial. And the reason I stopped here with our 7 factorial, 10 minus 3 gave us the 7 factorial, and then instead of saying 7 times 6 times 5 and using all that space and time, I stopped there so we can just cancel these out. So our 10 times 9 times 8, our numerator comes out to 720, divided by 6, so there's 120 different ways to choose the 3 volunteers. Okay, so we're going to start the next problem with some basics about playing cards. We know that there are 52 cards in a deck. There are 4 suits, hearts, spades, diamonds, and clubs, and 13 different cards in each suit. So if the order in which the cards are dealt is not important, how many different 5-card hands are possible? So if it's not important, we know we're going to be using combinations, not permutations. So we would write that problem. There are 52 cards. We only need 5. So that is 52 factorial over 5 factorial times 47 factorial, because 52 minus the 5 is 47. And if I write it all out, it's going to look like this. In my numerator, you can see I stopped at 47 factorial because I can see that the 47 factorial in the numerator and denominator can cancel. When I multiply out the rest of the values in the numerator and divide it by the denominator, it comes out to 2,598,960 combinations. Notice I put an example of what it should look like if you try to do it in your calculator. Be really, really careful including your parentheses in the denominator. I would pause the video and see if you can get the same answer by using your calculator. Remember, you go to the math button and you scroll over to probability and then down to the factorial option. All right, now we're going to look at example B. And how many 5-card hands are all 5 cards of the same color? So we know that they're either going to be red or black. So first we're going to pick the color. So we have 2 possible colors, and we only want one, either red or black. And then we're going to multiply. Now we're only using half of the deck now, so we have 26 cards to choose from, and we want 5. So if we wrote that out, it would be 2 factorial over 1 factorial 2 minus 1 factorial times our 26 factorial over 5 factorial 26 minus the 5 factorial. Okay, so I simplified it a little bit in blue. Now I'm going to cancel out my 21 factorials. And so when I multiply, I end up getting 131,560 combinations. All right, we just looked at examples when we multiply. So that's when we're finding the number of ways both an event A and event B can occur. On this slide, we're going to include OR. If we're looking at event A or event B, then we're going to add. So we have 38 novels, 18 are science fiction, 10 nonfiction, and 10 are mysteries. How many different sets of exactly 2 science fiction and 1 mystery can you read? So we have 18, so it's science fiction. So we have 18 that were science fiction, and we want just 2. We have 10 that are mysteries, and we're only going to be choosing one of those. Okay, so we had our 18 factorial in the numerator. 18 minus the 2 gave us the 16. 10 minus the 1 gave us the 9. When we simplify and we multiply everything out, we get 1,530 combinations. Now we're going to look at when it says at most. So how many different sets of at most 3 novels can you read? So we might not read any novels. We might read 2, we might read 3. So in this instance, we're going to add. We have 38 novels, and we choose to read 0 of them. We're really busy or something. 38 novels, and we managed to pick 1, 38, 2, and 38. And we must be summer. We have time to read. And when we work these all out, and we're going to add them up, it simplifies to 1 plus 38 plus 703 plus 8,436, and that comes out to 9,178.